Hello everybody, and hello from Tony. Just going to put Tony over here. Today we're going to read the C#6 draft specification by Mads Torgersen, Anders Halesberg and lots of other lovely people. Introduction. C#, pronounced C#, is a simple, modern, object-oriented and type-safe programming language. C# has its roots in the C family of languages and will be immediately familiar to C, C++ and Java programmers. C# is standardized by ECMA International as the ECMA 334 standard and by ISO IEC as the ISO IEC 23270 standard. Microsoft's C# compiler for the .NET framework is a conforming implementation of both of these standards. C# is an object-oriented language, but C# further includes support for component-oriented programming. Contemporary software design increasingly relies on software components in the form of self-contained and self-describing packages of functionality. Key to such components is that they present a programming model with properties, methods, and events. They have attributes that provide declarative information about the component, and they incorporate their own documentation. C# provides language constructs to directly support these concepts, making C# a very natural language in which to create and use software components. Several C# features aid in the construction of robust and durable applications. Garbage collection automatically reclaims memory occupied by unused objects. Exception handling provides a structured and extensible approach to error detection and recovery. And the type-safe design of the language makes it impossible to read from uninitialized variables, to index arrays beyond their bounds, or to perform unchecked typecasts. C# has a unified type system. All C# types, including primitive types such as int and double, inherit from a single root object type. Thus, all types share a set of common operations, and values of any type can be stored, transported, and operated upon in a consistent manner. Furthermore, C# supports both user-defined reference types and value types, allowing dynamic allocation of objects, as well as inline storage of lightweight structures. To ensure that C# programs and libraries can evolve over time in a compatible manner, much emphasis has been placed on versioning in C#'s design. Many programming languages pay little attention to this issue, and as a result, programs written in those languages break more often than necessary when newer versions of dependent libraries are introduced. Aspects of C#'s design that were directly influenced by versioning considerations include the separate virtual and override modifiers, the rules for method overload resolution, and support for explicit interface member declarations. The rest of this chapter describes the essential features of the C# language. Although later chapters describe rules and exceptions in a detail-oriented and sometimes mathematical manner, this chapter strives for clarity and brevity at the expense of completeness. The intent is to provide the reader, or listener, with an introduction to the language that will facilitate the writing of early programs and the reading of later chapters. Hello World. The Hello World program is traditionally used to introduce a programming language. Here it is in C#. And then there's some code. It starts using system semicolon, class hello, then an open brace on a line on its own, then static void main, open parenthesis, close parenthesis, space, and then an open curly brace on the same line. On the next line is console.writeLine, and then in parentheses, hello, world. Now it's interesting, this has a capital H and a capital W, but no exclamation mark. It would still have worked with the exclamation mark or with lowercase h or w, but it would have produced different output. Then there are two lines just with closing curly braces. Idiomatic C# wouldn't have had that second open brace on the same line as main, but we'll allow that. C# source files typically have the file extension .cs. Assuming that the Hello World program is stored in the file hello.cs, the program can be compiled with the Microsoft C# compiler using the command line csc hello.cs, which produces an executable assembly named hello.exe. The output produced by this application when it is run is hello world. The hello world program starts with a using directive that references the system namespace. Namespaces provide a hierarchical means of organizing C# programs and libraries. Namespaces contain types and other namespaces. For example, the system namespace contains a number of types such as the console class referenced in the program, and a number of other namespaces such as IO and collections. A using directive that references a given namespace enables unqualified use of the types that are members of that namespace. Because of the using directive, the program can use console.writeLine as a shorthand for system.console.writeLine. The hello class declared by the Hello World program has a single member, the method named main. Actually, it only declares a single member, but because it's a regular class, it also inherits the members to string, get hashcode, and equals, but never mind. The main method is declared with the static modifier. While instance methods can reference a particular enclosing object using the keyword this, static methods operate without a reference to a particular object. By convention, a static method named main serves as the entry point of a program. The output of the program is produced by the writeLine method of the console class in the system namespace. This class is provided by the .NET Framework class libraries, which by default are automatically referenced by the Microsoft C# compiler. Note that C# itself does not have a separate runtime library. Instead, the .NET Framework is the runtime library of C#. Program structure. The key organizational concepts in C# are programs, namespaces, types, members, and assemblies. C# programs consist of one or more source files. Programs declare types, which contain members and can be organized into namespaces. Classes and interfaces are examples of types. Fields, methods, properties, and events are examples of members. When C# programs are compiled, they are physically packaged into assemblies. Assemblies typically have the file extension .exe or .dll, depending on whether they implement applications or libraries. Then there's a much longer example which I'm not going to read out to you, but it declares a class named stack in a namespace called acme.collections. The fully qualified name of this class is acme.collections.stack. The class contains several members, a field named top, two methods named push and pop, and a nested class named entry. The entry class further contains three members, a field named next, a field named data, and a constructor. Assuming that the source code of the example is stored in the file acme.cs, the command line csc space /t:/library space acme.cs compiles the example as a library code without a main entry point and produces an assembly named acme.dll. Assemblies contain executable code in the form of intermediate language or IL instructions and symbolic information in the form of metadata. Before it is executed, the IL code in an assembly is automatically converted to processor-specific code by the just-in-time JIT compiler of the .NET Common Language Runtime. Because an assembly is self-describing unit of functionality containing both code and metadata, there is no need for #include directives and header files in C#. The public types and members contained in a particular assembly are made available in a C# program simply by referencing that assembly when compiling the program. For example, the following program uses the acme.collections.stack class from the acme.dll assembly. And then there's a program that does have a static void main method because it's an application, and it has a using acme.collections using directive. It includes code such as stack s equals new stack. That's using the acme.collections.stack class. If the program is stored in the file test.cs, then when test.cs is compiled, the acme.dll assembly can be referenced using the compiler's /r option. csc space /r:/acme.dll space test.cs. This creates an executable assembly named test.exe, which, when run, produces the following output: 100, 10, and then 1. C# permits the source text of a program to be stored in several source files. When a multi-file C# program is compiled, all the source files are processed together, and the source files can freely reference each other. Conceptually, it is as if all the source files were concatenated into one large file before being processed, except for some pragmas which have to come at the start of a source file, so we'll ignore that bit. Forward declarations are never needed in C# because, with very few exceptions, declaration order is insignificant. C# does not limit a source file to declaring only one public type, nor does it require the name of the source file to match a type declared in a source file. I think that's a bit of a jab at Java, where public classes, the compiler is allowed to say that they have to be in a file that's got the same name as the class. Types and variables. There are two kinds of types in C#, value types and reference types. Variables of value types directly contain their data, whereas variables of reference types store references to their data, the latter being known as objects. With reference types, it is possible for two variables to reference the same object, and thus possible for operations on one variable to affect the object referenced by the other variable. With value types, the variables each have their own copy of the data, and it is not possible for operations on one to affect the other, except in the case of ref and out parameter variables. That's unless the value types themselves contain reference type fields, where there can be two value types, both containing fields that then refer to the same object, and if you modify the object going via one of the value type variables, that would still be visible via the other one. C# value types are further divided into simple types, enum types, struct types, and nullable types, and C#'s reference types are further divided into class types, interface types, array types, and delegate types. The following table provides an overview of C#'s type system, and we've got some categories. So the category value types then has entries for simple types, which are the signed integral types sbyte, short, int, and long, unsigned integral types byte, ushort, uint, ulong, Unicode characters char, IEEE floating point float and double, high precision decimal decimal, boolean bool. Then there's the enum types, which are user-defined types of the form enum e braces, struct types, which are user-defined types of the form struct s braces, and nullable types, extensions of all other value types with a null value. Then under reference types, there's class types, the ultimate base class of all other objects, object, Unicode strings, string, user-defined types of the form class C braces, interface types, which are user-defined types of the form interface I braces, array types, single and multi-dimensional, for example, int open square brackets close square bracket, and int open square bracket comma close square bracket. Then there's delegate types, user-defined types of the form delegate int d open parentheses. The 8 integral types provide support for 8-bit, 16-bit, 32-bit, and 64-bit values in signed or unsigned form. The 2 floating point types, float and double, are represented using the 32-bit single precision and 64-bit double precision IEEE 754 formats. The decimal type is a 128-bit data type suitable for financial and monetary calculations, and that's actually a floating point type too, so I don't know why they don't count it as a floating point type there. C#'s bool type is used to represent Boolean values, values that are either true or false. Character and string processing in C# uses Unicode encoding. The char type represents a UTF-16 code unit, and the string type represents a sequence of UTF-16 code units. Then there's a table summarizing the C# numeric types, with an awful lot of numbers in. I'm not going to read that out. C# programs use type declarations to create new types. A type declaration specifies the name and the members of the new type. 5 of C#'s categories of types are user-definable: class types, struct types, interface types, enum types, and delegate types. A class type defines a data structure that contains data members, fields, and function members, methods, properties, and others. Class types support single inheritance and polymorphism, mechanisms whereby derived classes can extend and specialize base classes. A struct type is similar to a class type in that it represents a structure with data members and function members. However, unlike classes, structs are value types and do not require heap allocation. Struct types do not support user-specified inheritance, and all struct types implicitly inherit from type object. An interface type defines a contract as a named set of public function members. A class or struct that implements an interface must provide implementations of the interface's function members. An interface may inherit from multiple base interfaces, and a class or struct may implement multiple interfaces. A delegate type represents references to methods with a particular parameter list and return type. Delegates make it possible to treat methods as entities that can be assigned to variables and passed as parameters. Delegates are similar to the concept of function pointers found in some other languages, but unlike function pointers, delegates are object-oriented and type-safe. If you're a functional programmer, you might be thinking that delegates are a bit like functions. They are, but they're not quite as good. Class, struct, interface, and delegate types all support generics, whereby they can be parameterized with other types. An enum type is a distinct type with named constants. Every enum type has an underlying type, which must be one of the 8 integral types. The set of values of an enum type is the same as the set of values of the underlying type. C# supports single and multiple dimensional arrays of any type. Unlike the types listed above, array types do not have to be declared before they can be used. Instead, array types are constructed by following a type name with square brackets. For example, int open square bracket close square bracket is a single dimensional array of int. Int open square bracket comma close square bracket is a 2-dimensional array of int, and int open square bracket close square bracket open square bracket close square bracket is a single dimensional array of a single dimensional array of int. Nullable types also do not have to be declared before they can be used. For each non-nullable value type t, there is a corresponding nullable type t question mark, which can hold an additional value null. For instance, int question mark is a type that can hold any 32-bit integer or the value null. C#'s type system is unified, such that a value of any type can be treated as an object. Every type in C# directly or indirectly derives from the object class type, and object is the ultimate base class of all types. Values of reference types are treated as objects simply by viewing the values as type object. Values of value types are treated as objects by performing boxing and unboxing operations. In the following example, an int value is converted to object and back again to int. And then there's a class declaration and a main method declaration, but the important code is int I equals 123, object O equals I, that's boxing, and then int j equals, and then in parentheses, int O, that's unboxing. When a value of a value type is converted to type object, an object instance, also called a box, is allocated to hold the value, and the value is copied into that box. Conversely, when an object reference is cast to a value type, a check is made that the referenced object really is a box of the correct value type, and if the check succeeds, the value in the box is copied out. C#'s unified type system effectively means that value types can become objects on demand. Because of the unification, general-purpose libraries that use type object can be used with both reference types and value types, although generally generics are better. We might come on to generics in a little bit. There are several kinds of variables in C#, including fields, array elements, local variables, and parameters. Variables represent storage locations, and every variable has a type that determines what values can be stored in the variable, as shown in the following table. So, a non-nullable value type variable can only contain a value of that exact type. A nullable value type variable can contain a null value or a value of that exact type. A variable of type object can contain a null reference, a reference to an object of any reference type, or a reference to a boxed value of any value type. A class type variable can contain a null reference, a reference to an instance of that class type, or a reference to an instance of a class derived from that class type. An interface type variable can contain a null reference, a reference to an instance of a class type that implements that interface type, or a reference to a boxed value of a value type that implements that interface type. An array type variable can contain a null reference, a reference to an instance of that array type, or a reference to an instance of a compatible array type. And a delegate type variable can contain a null reference or a reference to an instance of that delegate type. Expressions. Expressions are constructed from operands and operators. The operators of an expression indicate which operations to apply to the operands. Examples of operators include plus, minus, times, divide, and new. Examples of operands include literals, fields, local variables, and other expressions. When an expression contains multiple operators, the precedence of the operators controls the order in which the individual operators are evaluated. For example, the expression x plus y plus z is evaluated as x plus y times, For example, the expression x plus y times z is evaluated as x plus y times z because the star times operator has higher precedence than the plus operator. Should be noted that x is still evaluated before y times z is evaluated. Most operators can be overloaded. Operator overloading permits user-defined operator implementations to be specified for operations where one or both of the operands are of a user-defined class or struct type. Then there's a table summarizing the C# operators, listing the operator categories in the order of precedence from highest to lowest. Operators in the same category have equal precedence. So in the primary category, we have an expression x.m, which is member access, x and then parentheses dot dot dot, which is method and delegate invocation, x square brackets dot dot dot, array and indexer access, x plus plus post increment, x minus minus post decrement, new t parentheses object and delegate creation, new t parentheses and braces object creation with an initializer, new braces anonymous object initializer, new t square brackets array creation, type of t obtain system.type object for t, checked brackets x evaluate an expression in a checked context, unchecked x evaluate an expression in an unchecked context, default t obtain the default of value type t, default value of type t, doesn't have to be a value type, and delegate braces, which is an anonymous function. When I talked about the object and delegate creation, I said about new t and then parentheses, and then there's new t parentheses braces for object creation with an initializer. There's also new t just with the braces and no parentheses. That's object creation with an initializer, but calling a parameterless constructor, or at least not passing any arguments explicitly to a constructor. The unary operators are plus x, which is identity, minus x, negation, exclamation mark x, logical negation, tilde x, bitwise negation, plus plus x, pre-increment, minus minus x, pre-decrement, t in brackets x, which is explicitly convert x to type t, and await x, asynchronously wait for x to complete. The multiplicative operators are x times y, multiplication, x slash y, division, x percent y, remainder. The additive operators are x plus y for addition, string concatenation and delegate combination, and x minus y for subtraction and delegate removal. The shift operators are x and then angle bracket left, y, which is shift left, and x angle bracket right, which is shift right, or close angle bracket. Then there's the relational and type testing operators. X open angle bracket y is less than, x close angle bracket y is greater than, and from now on I'm going to use less than to mean open angle bracket and greater than to mean close angle bracket, just for simplicity. X less than equal y is less than or equal. X greater than equal y is greater than or equal. X is t, return true if x is a t, false otherwise, and x as t, return x typed as t or null if x is not a t. Then we've got the equality operators. X equals y, which is equal, and x exclamation mark equal y, which is not equal. The logical AND operator, x ampersand y, integer bitwise AND Boolean logical AND. The logical XOR operator, x caret y, integer bitwise XOR and Boolean logical XOR. The logical OR operator, x pipe y, integer bitwise OR and Boolean logical OR. The conditional AND, which is x ampersand y, evaluates y only if x is true. The conditional OR, x pipe y, evaluates y only if x is false. The null coalescing x question mark y evaluates to y if x is null and to x otherwise. And I've just noticed there's a little typo in the specification here. It's got a capital X where it should have a lowercase x. Then the conditional operator, x question mark y colon z, evaluates y if x is true and z if x is false. Some people call that the ternary operator, but that just means that there are three operands. At the moment it's the only ternary operator, but its name is the conditional operator, or conditional question mark colon operator, to make it clear that it's not conditional AND or conditional OR. Always call it by its proper name because it makes it happy. Then finally there's the assignment or anonymous function operators. X equals y is assignment. X and then op equals y is the compound assignment supported by operators star, slash, percent, plus, minus, double less than and double greater than for shifts, ampersand, caret and pipe, and then in brackets t x equals greater than y, and that equals greater than is also known as fat arrow, and that's used for anonymous functions or lambda expressions. We'll see that fat arrow syntax later on when we talk about expression-bodied members, but it's only an operator when it's used as a lambda expression. Statements. The actions of a program are expressed using statements. C# supports several different kinds of statements, a number of which are defined in terms of embedded statements. A block permits multiple statements to be written in contexts where a single statement is allowed. A block is a list of statements written between the delimiters open brace and close brace. Curly braces those are. Declaration statements are used to declare local variables and constants. Expression statements are used to evaluate expressions. Expressions that can be used as statements. I'm sorry, my laptop decided to go to sleep. Expression statements are used to evaluate expressions. Expressions that can be used as statements include method invocations, object allocations using the new operator, assignments using equals and the compound assignment operators, increment and decrement operations using plus plus and minus minus operators, and await expressions. Selection statements are used to select one of a number of possible statements for execution based on the value of some expression. In this group are the if and switch statements. And I'm very much looking forward to C#8, where switch will become an expression. Iteration statements are used to repeatedly execute an embedded statement. In this group are the while, do, for, and for each statements. Jump statements are used to transfer control. In this group are the break, continue, go to, throw, return, and yield statements. The try-catch statement is used to catch exceptions that occur during execution of a block, and the try-finally statement is used to specify finalization code that is always executed whether an exception occurred or not. The checked and unchecked statements are used to control the overflow checking context for integral type arithmetic operations and conversions. The lock statement is used to obtain the mutual exclusion lock for a given object, execute a statement, and then release the lock. The using statement is used to obtain a resource, execute a statement, and then dispose of that resource. Below are examples of each kind of statement, and I'm afraid reading those out doesn't really work. So I'm going to just skip over all of those. Oh, what a lot there are. Classes and objects. Classes are the most fundamental of C#'s types. A class is a data structure that combines state, fields, and actions, methods or other function members in a single unit. A class provides a definition for dynamically created instances of the class, also known as objects. Classes support inheritance and polymorphism, mechanisms whereby derived classes can extend and specialize base classes. New classes are created using class declarations. A class declaration starts with a header that specifies the attributes and modifiers of the class, the name of the class, the base class if given, and the interfaces implemented by the class. The header is followed by the class body, which consists of a list of member declarations written between the delimiters open curly brace and close curly brace. The following is the declaration of a simple class named point. It's got public class point, that's the header, open curly brace, and then comes the body, public int x, y, semicolon, that's declaring fields, and then public point, and then in parentheses, int x, int y, open curly brace, this dot x equals x, semicolon, this dot y equals y, semicolon, close curly brace, and then comes the closing curly brace of the class. That's a constructor. Instances of classes are created using the new operator, which allocates memory for a new instance, invokes a constructor to initialize the instance, and returns a reference to the instance. The following statements create two point objects and store references to those objects in two variables. Point p1 equals new point, open parentheses, 0, 0, close parenthesis, semicolon, and point p2 equals new point, open parenthesis, 10, 20, close parenthesis, semicolon. The memory occupied by an object is automatically reclaimed when the object is no longer in use. It is neither necessary nor possible to explicitly deallocate objects in C#. Members. The members of a class are either static members or instance members. Static members belong to classes and instance members belong to objects, instances of classes. Then there's a table providing an overview of the kinds of member a class can contain. It can contain constants, which are constant values associated with the class. Fields, which are variables of the class. Methods, computations and actions that can be performed by the class. Properties, actions associated with reading and writing named properties of the class. That's a little bit self-referential, I think. Then indexes, actions associated with indexing instances of the class to make it look like an array. events, which are notifications that can be generated by the class, operators, which are conversions and expression operators supported by the class, constructors, actions required to initialize instances of the class or the class itself, destructors, also known as finalizers, which are actions to perform before instances of the class are permanently discarded, and types, which are nested types declared by the class. Accessibility. Each member of a class has an associated accessibility, which controls the regions of program text that are able to access the member. There are 5 possible forms of accessibility. These are summarized in the following table. Public means access is not limited. Protected means access is limited to this class or classes derived from this class. Internal means access is limited to this program or assembly. Protected internal is access is limited to this program or classes derived from this class. And private, access is limited to this class. And in C#7, one of the minor versions of C#7, there's also private protected, which is access is limited to this class, to this program, and only within classes derived from this class. So private protected is more specific, more restricted than protected internal. Type parameters. A class definition may specify a set of type parameters by following the class name with angle brackets enclosing a list of type parameter names. The type parameters can then be used in the body of the class declarations to define the members of the class. In the following example, the type parameters of pair are t first and t second, and it's got a declaration public class pair open angle bracket t first comma t second close angle bracket, and then it's got fields, public fields, which we don't like, called first and second, which are of types t first and t second. A class type that is declared to take type parameters is called a generic class type. Struct, interface, and delegate types can also be generic. When the generic class is used, type arguments must be provided for each of the type parameters. And then it's got an example with pair of int and string. So t first is int and t second is string. And it shows that pair.first is of type int and pair.second is of type string. A generic type with type arguments provided, like pair of int and string above, is called a constructed type. There's a lot of terminology around generics, around open, closed, constructed, all kinds of things, and you almost never need to know about it. Base classes. A class declaration may specify a base class by following the class name and type parameters with a colon and the name of the base class. Omitting a base class specification is the same as deriving from type object. In the following example, the base class of point3d is point, and the base class of point is object, and it's got just public class point, and then later public class point3d colon space point. Now they haven't put a space before the colon there, and almost every C# programmer I've ever seen does, because with public class point3d colon with no space and then a space point, that looks a little bit more like a case statement, or a case label rather. Anyway, a class inherits the members of its base class. Inheritance means that a class implicitly contains all members of its base class except for the instance and static constructors and the destructors or finalizers of the base class. A derived class can add new members to those it inherits, but it cannot remove the definition of an inherited member. In the previous example, point3d inherits the x and y fields from point, and every point3d instance contains 3 fields, x, y, and z. An implicit conversion exists from a class type to any of its base class types. Therefore, a variable of a class type can reference an instance of that class or an instance of any derived class. For example, given the previous class declarations, a variable of type point can reference either a point or a point 3D. And then it's got a little example that says point A equals new point 1020 and point B equals new point 3D 1020 30. Fields. A field is a variable that's associated with a class or with an instance of a class. A field declared with the static modifier defines a static field. A static field identifies exactly one storage location. No matter how many instances of a class are created, there's only ever one copy of a static field. A field declared without the static modifier defines an instance field. Every instance of a class contains a separate copy of all the instance fields of that class. In the following example, each instance of the color class has a separate copy of the R, G, and B instance fields, but there's only one copy of the black, white, red, green, and blue static fields. And then it's got public static read-only color, black equals new color 000, and so on, but then private byte R, G, B. So R, G, B are the instance fields, and black is a static field. As shown in the previous example, read-only fields may be declared with a read-only modifier. Assignment to a read-only field can only occur as part of the field's declaration or in a constructor of the same class. A method is a member that implements a computation or action that can be performed by an object or class. Static methods are accessed through the class. Instance methods are accessed through instances of the class. Methods have a possibly empty list of parameters which represent values or variable references passed to the method, and a return type which specifies the type of the value computed and returned by the method. A method's return type is void if it does not return a value. Like types, methods may also have a set of type parameters for which type arguments must be specified when the method is called. Unlike types, the type arguments can often be inferred from the arguments of a method call and need not be explicitly given. That's a bit of a silly way of saying it, I think. It says the type arguments must be specified, but they don't have to be explicitly given. I'd say that's how you specify them. But it basically means that you can give them explicitly, and sometimes the C# compiler can work them out for itself. The signature of a method must be unique in the class in which the method is declared. The signature of a method consists of the name of the method, the number of type parameters, and the number, modifier, and types of its parameters. The signature of a method does not include the return type. Parameters. Parameters are used to pass values or variable references to methods. The parameters of a method get their actual values from the arguments that are specified when the method is invoked. There are 4 kinds of parameters: value parameters, reference parameters, output parameters, and parameter arrays. A value parameter is used for input parameter passing. A value parameter corresponds to a local variable that gets its initial value from the argument that was passed for the parameter. Modifications to a value parameter do not affect the argument that was passed for the parameter. Value parameters can be optional by specifying a default value so that the corresponding arguments can be omitted. Now, please don't get confused between value types and reference types here. Even though there are value types and reference types, and value parameters and reference parameters, they're not quite the same. So a value parameter can still be of a reference type, and that means that the reference is copied into the value parameter when the method is invoked. I've got an article about that I'll link to in the video. A reference parameter is used for both input and output parameter passing. The argument passed for a reference parameter must be a variable, and during execution of the method, the reference parameter represents the same storage location as the argument variable. A reference parameter is declared with the ref modifier. The following example shows the use of ref parameters. Now that's a bit tricky to imagine, so I'm going to skip over it. An output parameter is used for output parameter passing. An output parameter is similar to a reference parameter, except that the initial value of the caller provided argument is unimportant. An output parameter is declared with the out modifier, and then there's an example. It's important that an out parameter is still using pass by reference. That can get you into trouble if you do some very odd things with the variable and end up modifying it from outside the method. You might be able to see that change. A parameter array permits a variable number of arguments to be passed to a method. A parameter array is declared with the params modifier. Only the last parameter of a method can be a parameter array, and the type of a parameter array must be a single-dimensional array type. The write and writeLine methods of the system.console class are good examples of parameter array usage, and then it shows their declaration. Within a method that uses a parameter array, the parameter array behaves exactly like a regular parameter of an array type. However, in an invocation of a method with a parameter array, it is possible to pass either a single argument of the parameter array type or any number of arguments of the element type of the parameter array. In the latter case, an array instance is automatically created and initialized with the given arguments. And then it has an example where it calls console.writeLine and then a string saying x equals braces 0, y equals braces 1, z equals braces 2, x comma y comma z. And that's equivalent to writing string s equals x equals that string, and then object square brackets args equals new object 3 in square brackets, args 0 equals x, args 1 equals y, args 2 equals z, console.writeLine s comma args. Just one tip: if you've got a params array of type object array, so object square brackets, then it can be tricky if the caller specifies null and expects that to end up as a single value within an object array, but actually it just passes the null reference. I've seen people get confused by that, and it's difficult. Method body and local variables. A method's body specifies the statements to execute when the method is invoked. A method body can declare variables that are specific to the invocation of the method. Such variables are called local variables. A local variable declaration specifies a type name, a variable name, and possibly an initial value. And then it's got an example. C# requires a local variable to be definitely assigned before its value can be obtained. For example, if the declaration of the previous I did not include an initial value, the compiler would report an error for subsequent usages of I because I would not be definitely assigned at those points in the program. A method can use return statements to return control to its caller. In a method returning void, return statements cannot specify an expression. In a method returning non-void, return statements must include an expression that computes the return value. Arguably, the inclusion of void was a bit of a mistake. Instead, the C# designers could have thought about a type like F# unit type to represent no particular value, but still be a type. That would be very useful for generics. Static and instance methods. A method declared with a static modifier is a static method. A static method does not operate on a specific instance and can only directly access static members. A method declared without a static modifier is an instance method. An instance method operates on a specific instance and can access both static and instance members. The instance on which an instance method was invoked can be explicitly accessed as this. It is an error to refer to this in a static method, because there's no instance to refer to. The following entity class has both static and instance members, but it's a bit boring, so I'm going to move on. Each entity instance contains a serial number and presumably some other information that's not shown here. The entity constructor, which is like an instance method, initializes the new instance with the next available serial number. Because the constructor is an instance member, it's permitted to access both the serial number instance field and the next serial number static field. The getNextSerialNumber and setNextSerialNumber static methods can access the next serial number static field, but it would be an error for them to directly access the serial number instance field. And then there's an example showing the usages of that class. Virtual, override, and abstract methods. When an instance method declaration includes a virtual modifier, the method is said to be a virtual method. When no virtual modifier is present, the method is said to be a non-virtual method. When a virtual method is invoked, the runtime type of the instance for which that invocation takes place determines the actual method implementation to invoke. In a non-virtual method invocation, the compile time type of the instance is the determining factor. A virtual method can be overridden in a derived class. When an instance method declaration includes an override modifier, the method overrides an inherited virtual method with the same signature. Whereas a virtual method declaration introduces a new method, an override method declaration specializes an existing inherited virtual method by providing a new implementation of that method. An abstract method is a virtual method with no implementation. An abstract method is declared with the abstract modifier and is permitted only in a class that is also declared abstract. An abstract method must be overridden in every non-abstract derived class. Then there's an example. It says the following example declares an abstract class expression which represents an expression tree node and 3 derived classes constant, variable reference and operation which implement expression tree nodes for constants, variable references and arithmetic operations. This is similar to, but not to be confused with, the expression tree types introduced in expression tree types, which is another section. Not a great example to use, perhaps. The previous 4 classes can be used to model arithmetic expressions. For example, using instances of these classes, the expression x plus 3 can be represented as a new operation with a variable reference to x, plus as the operator, and a new constant of 3. The evaluate method of an expression instance is invoked to evaluate a given expression and produce a double value. The method takes as an argument a hash table that contains variable names as keys of the entries and values as values of the entries. The evaluate method is a virtual abstract method, meaning that non-abstract derived classes must override it to provide an actual implementation. A constant implementation of evaluate simply returns the stored constant. A variable references implementation looks up the variable name in the hash table and returns the resulting value. An operations implementation first evaluates the left and right operands by recursively invoking their evaluate methods and then performs the given arithmetic operation. The following program uses expression classes to evaluate the expression x times y plus 2 for different values of x and y, but we're not going to look at that now. Method overloading. Method overloading permits multiple methods in the same class to have the same name as long as they have unique signatures. When compiling an invocation of an overloaded method, the compiler uses overload resolution to determine the specific method to invoke. Overload resolution finds the one method that best matches the arguments or reports an error if no single best match can be found. Then there's an example showing overload resolution in effect with some comments. And it says, as shown by the example, a particular method can always be selected by explicitly casting the arguments to the exact parameter types and or explicitly supplying type arguments. That's the case for that example because it doesn't use inheritance. Method overloading and overload resolution are very, very complicated. And the overload resolution part of the specification is one of the hardest bits to get right. And we haven't quite got it right yet. Other function members. Members that contain executable code are collectively known as the function members of the class. The preceding section describes methods which are the primary kind of function members. This section describes the other kinds of function members supported by C#. Constructors, properties, indexers, events, operators, and destructors or finalizers. The following code shows a generic class called listOfT, which implements a growable list of objects. The class contains several examples of the most common kinds of function members, and then there's a very long example. Constructors. C# supports both instance and static constructors. An instance constructor is a member that implements the actions required to initialize an instance of a class. A static constructor is a member that implements the actions required to initialize a class when it is first loaded. A constructor is declared like a method with no return type and the same name as the containing class. If a constructor declaration includes a static modifier, it declares a static constructor. Otherwise, it declares an instance constructor. Instance constructors can be overloaded. For example, the listOfT class declares two instance constructors, one with no parameters and one that takes an int parameter. Instance constructors are invoked using the new operator. The following statements allocate two list-of-string instances using each of the constructors of the list class, and one says new list angle bracket string bracket bracket, and the other says new list angle bracket string bracket 10 bracket. Unlike other members, instance constructors are not inherited, and a class has no instance constructors other than those actually declared in the class. If no instance constructor is supplied for a class, then an empty one with no parameters is automatically provided. Properties. Properties are a natural extension of fields. Both are named members with associated types, and the syntax for accessing properties and fields is the same. However, unlike fields, properties do not denote storage locations. Instead, properties have accessors that specify the statements to be executed when their values are either read or written. A property is declared like a field, except that the declaration ends with a get accessor and or a set accessor written between the delimiters curly braces, instead of ending with a semicolon. A property that has both a get accessor and a set accessor is a read-write property. A property that has only a get accessor is a read-only property, and a property that has only a set accessor is a write-only property or a mistake. Well, usually anyway. A get accessor corresponds to a parameterless method with a return value of the property type. Except as the target of an assignment, when a property is referenced in an expression, the get accessor of the property is invoked to compute the value of the property. A set accessor corresponds to a method with a single parameter named value and no return type. When a property is referenced as the target of an assignment, or as the operand of ++ or -, the set accessor is invoked with an argument that provides the new value. The listOfT class declares two properties, count and capacity, which are read-only and read-write respectively. And then it shows an example setting names.capacity to 100 and then fetching names.count and names.capacity. Similar to fields and methods, C# supports both instance properties and static properties. Static properties are declared with the static modifier, and instance properties are declared without it. The accessors of a property can be virtual. When a property declaration includes a virtual, abstract, or override modifier, it applies to the accessors of the property. Indexers. An indexer is a member that enables objects to be indexed in the same way as an array. An indexer is declared like a property, except that the name of the member is this, followed by a parameter list written between delimiters open square bracket and close square bracket. The parameters are available in the accessors of the indexer. Similar to properties, indexers can be read-write, read-only, and write-only, and the accessors of an indexer can be virtual. The list class declares a single read-write indexer that takes an int parameter. The indexer makes it possible to index list instances with int values, and then it gives an example where it adds Liz, Martha and Beth to a list of names and then accesses those by index. Indexers can be overloaded, meaning that a class can declare multiple indexers as long as the number or types of their parameters differ. Events. An event is a member that enables a class or object to provide notifications. An event is declared like a field, except that the declaration includes an event keyword and the type must be a delegate type. Within a class that declares an event member, the event behaves just like a field of a delegate type, provided the event is not abstract and does not declare accessors. The field stores a reference to a delegate that represents the event handlers that have been added to the event. If no event handlers are present, the field is null. The list of T class example declares a single event member called changed, which indicates that a new item has been added to the list. The changed event is raised by the onChanged virtual method, which first checks whether the event is null, meaning that no event handlers are present. The notion of raising an event is precisely equivalent to invoking the delegate represented by the event. Thus, there are no special language constructs for raising events. Clients react to events through event handlers. Event handlers are attached using the += operator and removed using the -= operator. And then there's an example attaching an event handler to the changed event of a list of strings. For advanced scenarios where control of the underlying storage of an event is desired, an event declaration can explicitly provide add and remove accessors, which are somewhat similar to the set accessor of a property. Operators. An operator is a member that defines the meaning of applying a particular expression operator to instances of a class. 3 kinds of operator can be defined: unary operators, binary operators, and conversion operators. All operators must be declared as public and static. The list of T class declares 2 operators, operator == and operator !=. Just to be clear, this is all referring to the list of T type that's earlier in the example, not system.collections.generic.list of T, which is what you normally think of when you see list of T. It defines those operators and thus gives new meaning to expressions that apply those operators to list of T instances. Specifically, the operators define equality of 2 list of T instances as comparing each of the contained objects using their equals methods, not the == operator, but equals, EQUALS methods. The following example uses the == operator to compare 2 list of instances. And then there's the example. I'll miss out the bit about the output of the example as I haven't told you about the example. Destructors, and I'm going to read all of these as finalizers because that's what the ECMA specification uses, and that's what I hope Microsoft starts using soon. A finalizer is a member that implements the actions required to destruct or finalize an instance of a class. Finalizers cannot have parameters, they cannot have accessibility modifiers, and they can't be invoked explicitly. The finalizer for an instance is invoked automatically during garbage collection. The garbage collector is allowed wide latitude in deciding when to collect objects and run finalizers. Specifically, the timing of finalizer invocations is not deterministic, and finalizers may be executed on any thread. For these and other reasons, classes should implement finalizers only when no other solutions are feasible. The using statement provides a better approach to object destruction, or at least object cleanup. It's not really destruction because a using statement doesn't destroy the object, it still exists afterwards. Structs. Like classes, structs are data structures that can contain data members and function members. But unlike classes, structs are value types and do not require heap allocation. A variable of a struct type directly stores the data of the struct, whereas a value of a class type stores a reference to a dynamically allocated object. Struct types do not support user-specified inheritance, and all struct types implicitly inherit from type object, or actually from type value type that then derives from object. Structs are particularly useful for small data structures that have value semantics. Complex numbers, points in a coordinate system, or key value pairs in a dictionary are all good examples of structs. I would add dates, times, date and time values, and all kinds of other things that NodaTime uses. The use of structs rather than classes for small data structures can make a large difference in the number of memory allocations an application performs. Can perform. For example, the following program creates and initializes an array of 100 points. With point implemented as a class, 101 separate objects are instantiated, one for the array and one for each of the 100 elements. An alternative is to make point a struct. Now only one object is instantiated, the one for the array, and the point instances are stored in line in the array. Struct constructors are invoked with the new operator, but that does not imply that memory is being allocated. Instead of dynamically allocating an object and returning a reference to it, a struct constructor simply returns the struct value itself, typically in a temporary location on the stack, and this value is then copied as necessary. With classes, it is possible for two variables to reference the same object, and thus possible for operations on one variable to affect the object referenced by the other variable. With structs, the variables each have their own copy of the data, and it is not possible for operations on one to affect the other. For example, the output produced by the code fragment below depends on whether point is a class or a struct, and it's got point A equals new point 1010, point B equals A, so that means copy the value of A into B, a.x equals 20, and then console.writeline b.x. If point is a class, the output is 20 because the values of A and B are references to the same object. If point is a struct, the output is 10 because the assignment of A to B creates a copy of the value, and this copy is unaffected by the subsequent assignment to A.x. The previous example highlights two of the limitations of structs. First, copying an entire struct is typically less efficient than copying an object reference, so assignment and value parameter passing can be more expensive with structs than with reference types. Second, except for ref and out parameters, it is not possible to create references to structs, which rules out their usage in a number of situations. Arrays. An array is a data structure that contains a number of variables that are accessed through computed indices. The variables contained in an array, also called the elements of the array, are all of the same type. And this type is called the elements type of the array. Array types are reference types, and the declaration of an array variable simply sets aside space for a reference to an array instance. Actual array instances are created dynamically at runtime using the new operator. The new operation specifies the length of the new array instance, which is then fixed for the lifetime of the instance. The indices of the elements of an array range from 0 to length minus 1. The new operator automatically initializes the elements of an array to their default value, which, for example, is 0 for all numeric types and null for all reference types. The following example creates an array of int elements, initializes the array, and then prints out the contents of the array. And there's an example with lots of punctuation. This example creates and operates on a single-dimensional array. C# also supports multi-dimensional arrays. The number of dimensions of an array type, also known as the rank of an array type, is 1 plus the number of commas written between the square brackets of the array type. So int square bracket is a single element, single dimensional array. Int square bracket comma square bracket is a two-dimensional array, and int square bracket comma comma square bracket is a three-dimensional array. The element type of an array can be any type, including an array type. An array with elements of an array type is sometimes called a jagged array because the length of the element arrays do not all have to be the same, although often they are. The following example allocates an array of arrays using int, and it's got int open square bracket, close square bracket, open square bracket, close square bracket, A equals new int, open square bracket 3, close square bracket, open square bracket, close square bracket. Array, open square bracket 0, close square bracket, equals new int, open square bracket 10, close square bracket. And then there are ones for A1 and 2 as well. The first line creates an array with 3 elements, each of type int, open close square bracket, and each with an initial value of null. The subsequent lines then initialize the 3 elements with references to individual array instances of varying lengths. The new operator permits the initial values of the array elements to be specified using an array initializer, which is a list of expressions written between the delimiters open and close curly braces. The following example allocates and initializes an int bracket bracket with 3 elements. Int open and close square brackets A equals new int open and close square brackets open curly brace 1, 2, 3 close curly brace semicolon. Note that the length of the array is inferred from the number of expressions between the open and close and curly brackets. Local variable and field declarations can be shortened further, such that the array type does not have to be restated. Int open square bracket close square bracket A equals, and then just open curly 1, 2, 3 close curly semicolon. And then it has an example showing what that's equivalent to. Interfaces. An interface defines a contract that can be implemented by classes and structs. An interface can contain methods, properties, events, and indexes. An interface does not provide implementations of the members it defines, it merely specifies that the members must be supplied by classes or structs that implement the interface. Interfaces may employ multiple inheritance. In the following example, the interface iComboBox inherits from both iTextBox and iListBox. And then there's the example. Importantly, that declares interface iControl, interface iTextBox, which derives from iControl, inherits from iControl, interface iListBox that inherits from iControl, and interface iComboBox that inherits from both iTextBox and iListBox. Classes and structs can implement multiple interfaces. In the following example, the class EditBox implements both iControl and iDataBound. Then there's an example. When a class or struct implements a particular interface, instances of that class or struct can be implicitly converted to that interface type. For example, EditBox equals new EditBox. iControl equals EditBox. Note that the type of control is iControl, the interface, but the type of EditBox is EditBox, the class. But you can still assign the value of EditBox to the variable control. And then iDataBound equals EditBox because EditBox implements both iControl and iDataBound. In cases where an instance is not statically known to implement a particular interface, dynamic typecasts can be used. For example, the following statements use dynamic typecasts to obtain an object's iControl and iDataBound interface implementations. Because the actual type of the object is EditBox, the casts succeed. And then there's object equals new EditBox, iControl equals, and then iControl in parentheses obj, and iDataBound equals iDataBound obj. In the previous EditBox class, the paint method from the iControl interface and the bind method from the iDataBound interface are implemented using public members. C# also supports explicit interface member implementations, using which the class or struct can avoid making the members public. An explicit interface member implementation is written using the fully qualified interface member name. For example, the EditBox class could implement the iControl.paint and iDataBound.bind methods using explicit interface member implementations as follows. And then it's got in the class EditBox, it's got void iControl.paint, parentheses, and then the implementation, and void iDataBound.bind, and then the parameter list, and then the implementation. Note that there's no access modifier at all there. You can't specify public, you can't specify private. It's just, there's no access at all for explicit interface implementation. Explicit interface members can only be accessed via the interface type. For example, the implementation of iControl.paint provided by the previous EditBox class can only be invoked by first converting the EditBox reference to the iControl interface type. Enums. An enum type is a distinct value type with a set of named constants. The following example declares and uses an enum type named color with three constant values, red, green and blue. And it's got enum color, open curly brace, red, green, blue, close curly brace. And then some examples using it, using color.red and color.blue. Each enum type has a corresponding integral type called the underlying type of the enum type. An enum type that does not explicitly declare an underlying type has an underlying type of int. An enum type's storage format and range of possible values are determined by its underlying type. This bit's important. The set of values that an enum type can take on is not limited by its enum members. In particular, any value of the underlying type of an enum can be cast to the enum type and is a distinct valid value of that enum type. The following example declares an enum type named alignment with an underlying type of sbyte. And that has enum alignment sbyte, open braces, and then it's got left equals -1, center equals 0, right equals 1. As shown by the previous example, an enum member declaration can include a constant expression that specifies the value of the member. The constant value for each enum member must be in the range of the underlying type of the enum. When an enum member declaration does not specify a value, the member is given the value 0 if it's the first member of the enum type, or the value of the textually preceding enum member plus 1. Enum values can be converted to integral values and vice versa using typecasts, and then there's an example. The default value of any enum type is the integral value 0 converted to the enum type. In cases where variables are automatically initialized to a default value, this is the value given to variables of enum types. In order for the default value of an enum type to be easily available, the literal 0 implicitly converts to any enum type, and so does 0.0 and other floating point zeros. Any 0 constant in the the Microsoft C# compiler is implicitly convertible to any enum type. Isn't that fun? Thus, the following is permitted: color C equals 0. Delegates. A delegate type represents references to methods with a particular parameter list and return type. Delegates make it possible to treat methods as entities that can be assigned to variables and passed as parameters. Delegates are similar to the concept of function pointers found in some other languages, but unlike function pointers, delegates are object-oriented and type-safe. And then there's an example declaring and using a delegate type named function. I'll read just a little bit. It says delegate double function with a capital F, and then in parentheses double X, and then just a semicolon. So there's no implementation. All it's saying is this is what a function looks like. An instance of the function delegate type can reference any method that takes a double argument and returns a double value. The apply method applies a given function to the elements of a double array, returning a double array with the results. In the main method, apply is used to apply 3 different functions to a double. And it's got examples of taking the square of a number, taking the sign value of a number, and then a multiplier, which in this case doubles the value. A delegate can reference either a static method, such as square or math.sign in this case, or an instance method, such as m.multiply in this example. A delegate that references an instance method also references a particular object, and when the instance method is invoked through the delegate, that object becomes this in the invocation. Delegates can also be created using anonymous functions, which are inline methods that are created on the fly. Anonymous functions can see the local variables of the surrounding methods. Thus, the multiplier example above can be written more easily, and then it shows an example with a lambda expression. An interesting and useful property of a delegate is that it does not know or care about the class of the method it references. All that matters is that the referenced method has the same parameters and return type as the delegate. Attributes. Types, members, and other entities in a C# program support modifiers that control certain aspects of their behavior. For example, the accessibility of a method is controlled using the public, protected, internal, and private modifiers. C# generalizes this capability such that user-defined types of declarative information can be attached to program entities and retrieved at runtime. Programs specify this additional declarative information by defining and using attributes. The following example declares a help attribute that can be placed on program entities to provide links to their associated documentation. And then it's got a public class help attribute deriving from attribute. The funny thing is that this help attribute class doesn't specify the valid attribute targets. I'm not entirely sure whether it's even valid, or maybe there's some defaulting that I just don't remember. All attribute classes derive from the system.attribute base class provided by the .NET framework. Attributes can be applied by giving their name, along with any arguments inside square brackets just before the associated declaration. If an attribute's name ends in attribute, that part of the name can be omitted when the attribute is referenced. For example, the help attribute can be used as follows. And then there's an open square brackets, help, and then in parentheses there's a string, close square bracket, and then public class widget. This example attaches a help attribute to the widget class and another help attribute to the display method, and I didn't explain that. The public constructors of an attribute class control the information that must be provided when the attribute is attached to a program entity. Additional information can be provided by referencing public read-write properties of the attribute class, such as the reference to the topic property in the example. And then there's an example showing how attribute information for a given program entity can be retrieved at runtime using reflection. When a particular attribute is requested through reflection, the constructor for the attribute class is invoked with the information provided in the program source, and the resulting attribute instance is returned. If additional information was provided through properties, those properties are set to the given values before the attribute instance is returned. And that's the end of the introduction. Doesn't it sound fun? And that's the end of our video. Okay. What's next?